Woohoo! All right. So, you should be looking at now my little setup over here. Can you still hear me?
Yeah.
Yes.
Yeah.
Great. So this is, it's a weight in the center here, and it's just got a string and it's going between the two. And the idea is that the weight really is in the center, so it's symmetrical. So we can say that the tension on this side is the same as the tension on this side. The angles are the same on both sides. And what I want you to do is to vary this angle, the angle between here and there. So this angle in here, you see, I kind of see my hand doing that. And so we're going to vary that angle and see how the tension varies. So what I want to start off doing is going through a range, and I've prescribed a set of ranges there. And I'll come back in a minute and we'll talk about them. But what I first want to do is when we put it straight down, this angle now is, in essence, 90 degrees, hanging straight down, and you could easily solve for that. If we said that this weight weighed 2 pounds, we could say that the tension on each side of the string would be half of that, correct? I mean, it's pretty straightforward. But what happens when we start to move it over here? And I'm going to put it back over here for a second. Hang it. Then you can see right here is a little bit of a spring. Maybe I need to move that up, but there's a spring that measures the tension. And so what I want to try and do is calculate that rather than measure. We don't always have little springs to do that. But what happens to the tension as we change this angle? And so as I make this angle steeper and steeper, this is now, you know, like 45. And if you're able to see this spring, you can see that it's starting to pull on that more and more. And the tension's going up, and it keeps going up. The question is, by how much and at what rate? You put that back down and come around again. So it probably was on the small screen, was it not? No, I probably should have put that on the stop sharing here. Let me go back to screen share. So what I'm hoping for right here is we're going to solve, you know, this is your resultants at this point, number 1, x1, y1, fx and fy. Clearly, the cosine of the tension in T1 for fx and for fy, it's T1 times the cosine of 90 plus theta. Because we always measure from the positive axis that we're trying to use, so fy, we measure from positive y. That would be this whole range here. So it would be this angle plus the 90 degrees. I assume Joanne talked about always using the cosine instead of the sine. It makes life easier. You don't have to worry about positives and negatives. So if that's a issue, we can talk about that a little bit later. So what I want you to do is solve for t in a meaningful way. It doesn't help to solve the fx equation because you don't know what the balancing equation is anywhere else. So you don't know what t is, and you don't know what w is, or you do know what w is, but you don't know what the x portion of the component there. So solve this equation, solve for t1, and then vary theta by these degrees. So set up a table of theta versus t1, and basically solve for those, and then create a plot of that, and then make a statement about what's happening as theta approaches 0. So if you have questions, now's a good time.
One of the questions that I saw in the chat, oh, sorry. One of the questions that I saw in the chat was like, do you want us to use engineering paper for this?
Yes, please.
Okay.
So as I said in my announcements, if you do everything on engineering paper and then scan that in, that's how to do it. It took me about an hour and a half to do all of this lab. So we're going to be a little pressed because if I do it in an hour and a half, that's usually what I call instructor time versus student time. Students usually take a little longer, so we'll see how far we get. Okay, there. I can't. Sorry, I didn't see the chats.
Do we know the
I can
weight?
put the. So the weight we're just going to assign is 2 pounds. We're just going to arbitrarily make it 2 pounds. It's about 1.5 pounds. It's 2 pounds. The 2 pounds should make life really easy for the math. Yeah. Who did that come from? So from Daniel, you asked about what is the question mark? The answer is we don't know. That's the problem. We don't know what Fy is because we don't know what T is, even though we know what cosine, even though we know theta. So you need to solve the problem starting with the Fy rather than the Fx.
What about breaking into little groups so we can work together?
Absolutely, I can do that. Let me, some people hate it.
This is less than inspiring. So, I mean, yeah. Without being able to touch it, I'm like, oh, bummer.
Working in groups, breakout groups would be great.
Yeah.
Okay. Let's see. About 3 of you.
Worst case scenario, we just do the same thing we're doing now.
Yeah, right.
Yeah. All right, here we go. I'm just going to do it randomly, so off you are.
Right. Yeah.
Yeah, like I said, big experiment here.
Hey, Rob.
Hey, Andrew?
Yeah.
Are you able to go in and out of
So,
breakout rooms?
I have one that says going to breakout room 4, but I don't think I have control to be able to switch to different breakout
Let me see
rooms.
if I can make you a co-host.
Okay. But I guess I could join breakout room 4 and then I could hop back out and maybe you could place me into a different one after.
Yeah, let's see what happens.
Okay. I'll join breakout room 4.
All right. And you're here with me, Isaac.
Rob. So I was just in breakout room 4. They were all good.
You seem to be going along. I'm trying to figure out how to make you move around. Let me see participants. Breakout rooms. Hold on a second. Where are you? Let me move you to room 5.
Okay.
Nobody's here. All right. Andrew's still there. Oh no. Andrew, you there? Hello? Yeah, he's gone. There you are.
Hello.
Are you on deck for questions?
Sure.
Our group isn't sure if we need to use the x equation. Are we only using the y equation?
Right. Well, you guys are solving for T1,
Correct.
and if you use the x equation, you have two unknowns in one equation, so it's
Okay.
impossible to solve. Which is why we got to start with the y, because we're given our weight.
Okay.
So now we have one unknown, one equation, and we could calculate our T1.
Rob
That-
or Andrew, can we steal you for breakout room 9?
Yeah,
I'm
I
about
just
to jump in here. You want to go in, Andrew?
you could go for it. I could keep helping David.
Okay, thanks. That makes sense to me. I just wasn't sure if we could just throw it out. It seems like you don't need it at
And
all.
Rob, will you bring me back into breakout room 9 when you do?
So Isaac, we have a button for that. There's a button near the bottom where it says breakout room, and
Oh,
then
we
you can
do?
hit join. Yeah.
Oh, hell yeah.
Yeah, you
Yeah.
should join there.
Now I don't know how Robert does it. I'm sure you have different buttons, but
Yeah.
there he goes. So Andrew, that's kind of what we assumed. I just wanted to make sure that that was okay to, like, you just don't use that equation. You just throw that out.
Yeah, and just like in any math, like you see your knowns, your unknowns, and then say, okay, what's the information I have, and based off of that, okay, how do I get my variables? So yeah, in this circumstance, the fx equation doesn't really do anything for you.
Okay.
You need to use fy, and you'll find that a lot in statics. You have to decipher, okay, I'm given the angle, so I could use these set of equations. Oh, I'm given just this force, now I have to use these equations, and then you have to work inside out sometimes.
Cool.
But-
Okay, I think that answers it. So we just don't need it. We logicked out. We just can't use that one, so we're going to use the other one.
True, right. And
Okay.
T1's true, whether you're talking in terms of f of x or f of y. It's just with the information given, we could solve for T1 using that f of y. That makes sense, because technically, T1 should be the same whether you're referring it in f of y equation or f of x equation.
I guess. I mean, I guess I am honestly not sure about that. You're telling me that, but I'm not sure that we've gone over that yet. Okay.
Well, like so when you look at f of y, when you change the angle, which is the whole point of this,
Yeah.
you're going to change basically with the setup, and then it's going to change, okay, the total fy versus the total fx force. And maybe something about this is, hey, is T1 constant through every angle, or hey, is T1 changing? And those are kind of something that when you plug it in and you sort of get some numbers, you'll be able to assess.
Well, I mean, we did it. We have our graph and everything
Nice.
Yeah, it's more of a theoretical question of, like, it looks like there would be a horizontal component to the T, to the tension, but I guess we're saying that
Right.
the vertical like gravity is like the only thing that's pulling. Is that the idea?
Yes, gravity's pulling. But there is sorry. So I think I understand your equation now. So there is a force in the x direction, right?
Yeah.
Yeah. So we know that. But basically, all I was trying to say is, you can't solve for that until you know what T1 is. So you solve for T1 for the given angle in your y component, and then in that given angle, you can then take that T1 value in that angle and then plug it into your f of x, and then find your f of x force.
Okay.
Does that make sense?
Yeah. I just we don't have to do that, right? That's actually not asked of us, right?
Right. Yeah.
Okay.
No.
Okay.
That's not asked.
Cool. Got it.
Yeah.
Okay.
And
I'll go.
what was your graph shape? Just wondering.
I think we feel pretty good about it. It's like that.
Perfect.
Yeah. And so, like, as the angle goes up, the T1 force falls, what is that? Logarithmically? Like, it approaches 1 but never gets there?
Yeah. Totally.
Cool.
Cool.
All
Man.
right. Thanks, man.
Of course.
Hey, Andrew, you still there? So I'm gonna give them a couple more minutes and then we'll slug on to the
Cool.
next part.
Yeah, so is there a way to allow me to like jump in and out of breakout rooms? You're saying I have to be like co-host or something?
I think I needed to do that earlier.
Okay.
So next time. So I'm so sorry.
No, it's a learning process. I don't know what I'm doing either.
This, yeah, when Joanne said, "Oh, we're going to do this," I started thinking about this like in May, thinking like, "How am I going to do this?"
Yeah.
So,
And yeah, like you were saying, Statics Lab is already like not many places offer it. And then now also making it all online too. It's like, yeah. But I think it's worth it though. And it is a very like foundational course. And I think a lot of kids get through some of the stuff without maybe conceptually really getting it. So like the lab helped me a lot. It just connect those dots.
yeah, it's funny. It serves some people really well, and other people is just sort of a drudgery.
Yeah.
So it's a full range of abilities. But yeah, for instance, this exercise, the whole point is to develop a sense of the fact that as that weight tries to come up to be level, you can never get that string flat.
Right.
It just can't happen. So
Yeah. Hopefully you'll see that. I think they will. That was like one of the main things I was trying to tell them. Try to predict what the shape of your graph's going to be like before you do it, and then try to understand why. But yeah. Hey,
yeah,
so
it's interesting.
was your work shut down at all, or have you been?
I've been working. I've had to work mostly at home. I do get special dispensations on occasion to go into work, particularly when I need to use like the machine shop or something.
Right.
I've I could show you my little mini shop to the right of me. I've got my oscilloscope and laptop and doing mechanical stuff. So
Cool.
I've been surprisingly productive.
Nice.
I thought it would be, oh my gosh, we're just going to do training videos from now until eternity.
Yeah, no, totally.
But that hasn't been the case.
Cool. Yeah, that's awesome. Yeah, I did. It's been a crazy year, man. Just a lot of ups and downs, and it's like, COVID was the biggest thing that's ever happened, and then now it's like it's like being overshadowed by other stuff, and I don't know. It's crazy, crazy times.
Yeah. I hope the end result is a good one.
Yeah, totally.
So you still in Watsonville? You're still working at the same place you were working at before?
Yeah, and actually, I've also been able to be pretty productive because it's all online now, and I don't have to commute or really be at a place. I'm able to pretty much work full time there, and then also go to school. So it's actually, and like the way where I'm at now, I really only have like two classes I need to transfer. So I'm taking materials, and that's like my big engineering class, and then the other ones are, pretty easy. So it's just, yeah, it's really allowed me to make a little more money actually while I go to school.
Yeah, I'm curious as to how Carl's going to do his labs as well.
Yeah, so we'll see. And he because I work today after this, I asked him if I need to be there, and he said you could do it asynchronously. And I'm just thinking in my head, oh, lab, you're supposed to work in groups, and I don't know how that's gonna work. But yeah, he said we're gonna go week by week, and we'll make it work no matter what. So yeah, we'll see.
Well, he's a really good teacher, so
Yeah.
I'm sure whatever happens, it's going to be awesome. So
Yeah, and he's good with all the technology too, and being able to post all his notes from OneNote and everything. Yeah, I don't know if you've ever used like a Surface Pro or a tablet and used OneNote, but it's a really cool way to share screen on Zoom, where it's basically you have a whiteboard and you can do whatever you want on it.
I got to figure that out. I should talk to him. Okay, I got to go join Breakout Room 8. Somebody's asking for help.
Okay.
Hi.
Hello.
I just came in.
Huh. How's it going?
Good, how are you?
Good.
Should I
Do you have
join?
any questions or anything, or are you guys just done with your breakout sesh?
Oh, I forgot that there was a lab 8 a.m.
Oh, okay.
I
You just got here.
Yeah.
Okay. Yeah, no worries. So if you go on Canvas, on the modules page for today,
Uh-huh.
you'll see all the different stuff we're doing, and we actually the whole first part of the class was just kind of icebreaker, getting to know everyone. So we really just started. So yeah, no worries. And yeah,
Awesome.
just start with part 1A, and basically what we're trying to do is understand how the forces change when we change the angle that something's hanging from it. So
So,
yeah, I don't know if you have it in front of you, but when you get to part 1A, you'll see a little pulley or little weight hung by two strings,
mhm.
and there's a theta, and that's what's changing. And it's just trying to say, hey, like as theta approaches to zero, like what happens um, to the forces and to the string. And yeah, so here, let me see. Also, I could share my screen if that makes it easier.
Okay,
Um,
thank you.
okay, huh. I actually can't share my screen right now. Rob has to give me access. But yeah, so just I would say just yeah, go on Canvas, check that out, and then he wants us to create a table between theta and the force T1,
Uh-huh.
and he'll give you a little equation for the force in the x direction and force in the y direction, and you'll come to the conclusion that you need to use the force in the y direction because then you only have one unknown, and you're able to solve for T1.
Gotcha.
Yeah.
So this is due by today, 11 a.m.
So he said we're gonna go and see how far we get, and then based off of that, he's gonna tell us what to turn in and what not. Um, so don't worry too much. But yeah, this should be one of the things that you turn in. And they're actually he's about to get out of the breakout groups and come back to this main spot, and then yeah, he'll be able to fill you in. If we go into another breakout room, I could have Rob talk to you directly, and then that way you could ask him the questions you need.
Got it.
Yeah. I know the 8 a.m. lab's pretty hard.
Yeah, and I just got added to this one, and then somehow I thought there was a lab 9 a.m.
Right, like reasonable people.
Yeah.
Yeah, I agree.
Uh, yeah. Mm.
Oh, he's not back yet. Andrew, is there going to be a time when Robert's going to do another demonstration?
Yes.
Okay, cool.
So yeah, I think there's 3 parts to this lab, and basically each time he's gonna do a little demonstration. You're gonna break out and try to do it. He'll kind of recap and then we'll move on to the next thing, and he'll do another demonstration. It's kind of how it's going to be.
Yeah, cool. I think our group was done with part A, so we're on standby here.
Cool. Yeah.
All
No
right.
worries.
Thanks.
Alrighty. I may call everybody back in a little bit to move on to the next section. Hey, you guys, Zoom guys, I usually do manual assignment of breakout rooms. If I bring everybody back and then put them back in automatically, do they go back to the same locations, or are you guys going to have different partners every time?
I think you could control that. I'm not totally sure though. I haven't really hosted a Zoom session before, but
I
go
actually,
ahead.
sorry. I was
No,
just
go
gonna
ahead.
say I actually just clicked on breakout room and it said that I'm still assigned a breakout room too, so I can just join it back.
Yeah, I think, well, I'm curious to bring everybody back. I have to close all the rooms, otherwise people stay in those rooms.
Oh, okay.
What I'm trying to do is bring everybody back to give the next piece of instruction. So you guys aren't sitting, clearly you're done, right?
Yeah.
So I'm, hoping to let you guys move forward, but in order to do that, I don't want to give the instruction multiple times. So let me yank everybody back, and we'll go on to the next piece and see what happens. So. You can also, of course, David and Marcin, and Daniel and Yo, you can look at the canvas. I think you should be able to look at the next part of the assignment on Canvas. So part 1B should be there.
Hey, Robert, could you it says I'm not allowed to screen share. It says host disabled participant screen sharing.
Yeah, it's interesting. Somebody in one of the breakout rooms was able to screen share.
Yeah, I was able to, and then I accidentally left the whole meeting and then rejoined it, and now it won't let me. Oh, there it goes. Cool.
I just gave everybody rights, and hopefully everybody will behave.
Nice. Yeah. So this is the next one, right? Lab
So if
one.
you want to move on to the next, yeah. So this is the next one. Let me share that. And all right, so this next section, is everybody back? I think everybody's back. This next part, what I'm looking for is to determine what you need to know in order to solve a particular problem. What I see a lot of times when students attack these problems is they feel a huge need to have every piece of information about the problem to solve it. And that wastes a lot of time and isn't always necessary. Or probably more important, in the real world, you don't always have all the information. So the question is what pieces of information do you need to know in order to solve a problem? The example I give here in this first one here is that in order to solve, what did I say? If I wanted to solve for the tension in either T1 or T2, I think I'm talking about. So I just basically initially start here, and I have the 3 points, point 1, 2, and 3, and I did the summation of the forces at each point in the X and the Y, and those are the equations that are available to you. So if we look at that first one, come again?
Could you mute all quickly?
Yeah. Let me find it. Did I get everybody muted? All right.
No, it's under the manage participants button. It should be mute all.
Yeah, I said that and it had all kinds of. Everybody should be muted now. Yeah, okay. One or two people are resisting, I guess, or something. Anyways, the first point, I give the equations here. You have fx, which would be the component in this direction along the x, and it would be a function of theta x1, because you would measure it from the positive x. So this is why it's theta x1. So you measure from positive x, and it's the cosine of that angle, plus fx1. Excuse me, I'm bungling this. Let me start again. So we have fx1, and then we also have the component of t. So at this point, we'd have fx in this direction, and then we would have a fy in this direction, and those two things added together in the fx direction, the x direction, have to equal 0, which is what we've got here. And you do the same in the y. And I've done this for all 3 points. So each of those points, this is the equations you have available to you. So in order to solve for any of these things, if you look at each of those equations, there's 3 unknowns. We don't know what the angle is, we don't know what the component at the point is, and we don't know what the tension in the string is. So we have 3 unknowns in each of these. And in this equation, set of equations, we have 2 equations and 3 unknowns. And actually, if we add in the next equation, we actually add another unknown because we now have fy and theta y. So we add 2 unknowns. We end up with 6 unknowns and 2 equations. So we clearly can't be solved. So the question is what pieces of information do you need to solve this? So if we look at the first one here, in number 1, we can solve. What did I ask for solve for? So we assume that we know the weights in each of these situations. In this case, I know the weight. I said it was 2 pounds, just as in the last equation. And if I wanted to solve for we're trying to solve for all the forces in the system. So the question is what do I need? In this first one, what I say solution 1, by having values of the tension and theta y, or the geometry between x1 and y3, or 0.1 and 0.3, can solve that. And so what I'm saying is that in order to solve for all the forces in this equation, or in this system, I have the weight. If I know T1 and this angle here, I can solve for T2 and the angle as well. I can solve all of that by having just theta and T1. And so the question is what other pieces of information would allow me to solve the entire system as well? And that would be T2 and theta x2 here. That would allow me to solve that. And I do that. I give the equations. So that would allow you to solve for all of that. So an example would be, as I said, here at 0.1, if I know T1 and I know this theta, I can solve for the components in T1. I can solve for the x component and the y component. And once I know that, at 0.3, I'll have the weight in y, and I'll have the T1 component in y, and then the only remaining component I don't know is T2 in the y direction. So I can solve for that. And once I've solved for that, then I can compare the x component of T1, because I know that angle, and then I can compare that to solve that for the T2 x component. I don't know if that's making sense. I wish I had a whiteboard. That would be my huge desire to be able to write this down for you so you can see how this is happening. But it allows you to solve for everything by just knowing T1 and theta y1 here, or theta x1. It's the same, basically the same thing, just looking at it differently. And so I said that there are 3 different ways to do that. You could also alternatively know theta x2 and theta y1 as well, and the weight. So again, the weight is the one thing that we're assuming that you know for sure. And then you can solve for T1 and T2 because you know the geometry of all of these. The point of this exercise is to get you to realize that you don't need to know all the information. A lot of times, like what I told is that people want to fill in everything to get to the final answer. And sometimes there's a more direct path to solving for just T1 or just T2, or knowing what the angle needs to be in order for T1 or T2 to be some particular value. So what I'm hoping for, let me change my video. Let me stop sharing. I'm going to move this to my next one. So this is the setup. I think it's bigger this time than the last time, if I'm not correct. I think I got this right.
Yeah, this looks good.
So what we're trying to do is we're trying to solve for T3. And if I know the weight, you know, you can just imagine these are each 2 pounds. And I know the weights. What pieces of information do I need to have to solve for the tension in this string? Is it just the geometry? Is it the geometry and the tension that's being measured here? Or is it the tension and the geometry? So the question is what pieces of information would you go and measure if I told you, well, I want you to calculate this tension here? What would you need to measure? Would you measure the geometry, all the geometry, or would you measure the tension and then one side geometry, or the tension and one side geometry? So there's multiple ways to do this, but the question is what's the most minimal amount of information that you would need to go and measure if you were trying to solve for this tension in this middle rope? What would you use? And this is a bit of a stretch. This is not, this isn't normally how we approach these problems, which is why I'm trying to do this in a lab rather than in a course. I want you to kind of trying to develop a sense of what's required to solve a problem rather than just taking all of the math and writing it all down and just grinding through it. So I'm trying to get you to start to think about there are faster ways to solve these problems than just grinding everything out. If you stop and think about it, and Joanne's going to go through this, she's got a nice step-by-step method that helps develop this, but I'm just trying to get you started here to thinking about it. What do you need?
Looks complicated.
It is not as bad as you think. Okay, I don't know who's sharing there, Jason. If you could stop sharing, it looks like you did the correct thing there, from what I can tell.
Oh, cool.
If you could stop sharing so I can share.
Oh, am I taking over something?
Yes.
I'm completely in the dark here. I have no idea how to undo that.
You should be able to see this again, right?
Did you fix it, or do I need to do something?
What's that?
Did you fix it, or do I need to do something?
I think
I
you just
think
need
I
to
fixed it.
mute yourself.
So what I'm asking for, again, is to come up with 2 ways to solve this with the least amount of information. So what it really requires is that you write down the equations probably at some of these points, in the particular points 3 and 4, because if you're looking for T3, you're definitely going to want to know what's happening at these points. So if you draw, what's happening at point 4, you're going to have T3 and 2 components of T3, X and Y, and you're going to have T1, and you're going to have 2 components of T2, X and Y. And so the question is how do you solve for those things? So you're also going to have W at point 4. So give that a thought. I'm going to put you guys in breakout rooms. Well, let me stop for a second and stop sharing the screen so I can see you guys better. Does that sort of make sense? Can you follow that? Or you're totally lost?
So one question that occurs to me is, if we do break out into groups, are we able to sort of raise our hand for questions and maybe have you come visit the room?
Somebody did that. Go ahead.
You can leave and rejoin the room at will. When you leave a room, there will be a button down at the bottom that says you can rejoin in the same room.
I see. Okay,
I
so
think
it'll be
there's
like
also a way to ask for help. Somebody.
There is
You
also
can
an
also
ask
call
help
for
button.
help.
Cool.
Yeah,
There's a little button on the taskbar that lets you call for help.
Okay.
Right.
Yes. All right. So I'm going to put you back in the breakout rooms. It looks like you're all going to go back to the same rooms, I assume. So let's give that a try. So Andrew, I'm going to toss you in a room shortly, but it doesn't look like we're going to get to part 2. So not that I'm surprised. I'm not hearing you, Andrew.
Oh, sorry, my mic was muted.
There you go.
Sorry. So the 3 tension problem that we're doing right now, that's still part 1.
Yes.
Part 1C.
It's still part 1.
Okay.
Part 2 is all drawing, and
Right.
we're just not going to get to it.
Okay.
I'll probably talk about direction angles. Joanne wanted me to talk about direction angles, so try and get people to understand direction angles.
Yeah, totally.
All right, I'm going to go visit some rooms. You want me to stick you in a room?
Yeah, just stick me in a room.
Let's put you in room 2.
Okay.
Hi, can I get signed into room 2?
Me
Okay.
too.
Yeah.
So how do you say your name? Let me get your name correct.
Yoji?
Yoji? Okay. Thank you. Sorry, sometimes I struggle.
It's all good.
Okay, thank you. So Elizabeth and Hermes, you guys are happy not being in a room. Somehow you're not in a room. I'm not quite sure what happened there.
I was in room 8 and then it didn't ask me to join the breakout room this time.
Okay, I'll put you back in room 8 now.
Thank you.
So we're just about out of time here, which is why I'm doing this.
So
Hey,
we did
Robert.
not
Yeah,
get
go
that.
ahead. Yeah, Robert, we had a pretty major problem with that. I think there's a pretty big gap in understanding where we can like look at specific forces and stuff, but we don't have the tools to like relate everything yet. And I think we're missing some pretty big gaps in like how to understand this.
That's okay. That's part of my learning process as to where you are and part of your learning process to know where you need to be. This was no doubt, this was a difficult part. I kind of knew it would be hard for you guys. I wanted to see what would happen. We're not going to get to part 2, the drawing part at all today. So that's, you don't even bother handing that part in. I will go easy on this second part. Do what you can. If I can describe real quickly what needs to happen in part 2. But more importantly, what I really want to say is you know, this is the end of class. I'm going to hang out for another 45 minutes or so we can work this if you want. But I don't know what everybody's schedule is, and I don't feel that you need to be pinned to be here. But I'm available for the next 45 minutes. The way that I wanted this approach is that, let me go over and change screens real quick. And where is that? Hold on. Well, there are basically three ways to solve for this. One is to know this tension, the angle of this rope, and the angle of this rope. With those three pieces of information, you'll be able to solve for it. And you can do the same on this side. You know the tension, the angle, and the angle, you can solve for T3. And then lastly, the last way to do this is to know the angle of this, the angle of this, and the angle of this. And knowing those three pieces of information will also allow you to solve for everything.
By angle, do you mean the full angle, or we can also just know a component of it, right?
Yeah, or the ratio of the components, yes. Ultimately, the angle allows you to solve for the components, and if you do a static summation at any point above the weights, that's how you'll get there. So knowing those pieces of information, you do the sum of the points at 0.2, I think 0.3 or 0.4, you'll have an answer.
Can I make a point too?
Oh, absolutely, Andrew, please.
So I think the big thing here too, if you look at the paper or the diagram, so although we're given x1, y1, x3, y3, and they're just like dummy variables, you could treat those as real numbers in a sense, and really try to understand what a direction angle is and what it describes, and then what you can find from figuring out your lengths between each force and relating those two geometry pieces. Because really you could come up with equations that relate your, let's say, your T1 force with the cosine of the direction angle x1, and then you can also rewrite that same thing relating the distances. And I think that would help. I'm not sure if that's the best way to describe it, but I don't think everyone was getting that per se.
Yeah, I have a feeling this was a bit of a hard sell today. Again, I kind of take that into consideration when I'm looking at what you hand in. You have an hour to hand this stuff in. But again, like I said, anybody who has to go at this point and needs to go because this is the end of class, you're free to do so. Andrew has taken my labs before. Generally, people end up staying, half the people end up staying late because they're trying to finish stuff up. It's not uncommon, and I'm going to continue to do that. But at the same time, you're free to go at this hour. So I don't want to keep anybody. I don't know what your other class schedules are.
Rob, I have a question.
Yeah.
I couldn't find a place to submit the work online.
Goodness. All right. Well, that's definitely a fault of mine. I was under the impression that when I said you could submit on PDF, that somehow in Canvas could do that. You can just attach it in an email to me, and that would be sufficient.
Okay, sounds good.
All right. So I figure out the more appropriate way to make that happen.
All right.
Sorry about that. I thought it was straightforward, but okay. And again, I apologize. Well, I sort of apologize. It was definitely a difficult problem, no doubt about it.
That might be a Canvas issue. Like, we can see the assignment, but normally there's a button for like submit assignment, and we don't have that.
It's definitely a Canvas issue.
If you go to grades, it's usually there.
You can clearly see that what I'm trying to do in this class, or this lab, really, is to get your brains thinking. That's really what I want to do, is to get you to think outside the box, to stop thinking about just solving math problems. That's the whole point of this lab. It isn't, we do have a whole math section. That's what Joanne's covering. She's covering how to solve those things and how to approach problems. And I'm trying to get you to think about it. Think about it in another level. So
It's
hopefully I achieved
Hey,
that.
Rob.
yeah, you had a hard task, Rob, honestly, because without the physical, tangible, we're playing with weights, we're playing with strings, we're trying different things, we're moving pegs around. That's a really hard. Yeah, you had the right wording. It's a hard sell without being able to touch it. Yeah.
Yeah, agreed.
Can I share my screen real quick?
Yeah, absolutely.
Okay.
Please.
Just a quick thing, by the way, Rob. I noticed that on the labs it says submitting on paper, so I think that's why we can't submit online, is because it thinks
Okay.
we're supposed to turn this in to you.
Okay.
Um,
I will fix that for next time. If you guys could email it in the, by using the Canvas email, I'll get it.
all right. Can everyone see my OneNote page?
I am able to.
You're good.
Cool. So this is what I was trying to say about you can represent the same thing in two different ways. The top line uses our direction angle, but then we can represent that direction angle with geometry by using our distances. And so now we could find out more information in the problem, or we can keep on tinkering with the equations to have them workable into information we do have. So that's just what I was trying to say about using your distances to kind of represent your angles.
Andrew's got a good point there. You can see that, theta x1 is the equivalent of that, what's down in his paragraph there. That's basically the positions that creates the geometry versus just knowing the angle. They're more or less one of the same. A lot of times in these problems, they present it as a ratio. It might do a 3, 4, 5 slope, 3 on one side of the right triangle, 4 on another, and then 5 on the other.
Right.
It's another way to do that.
All right.
It all boils down to kind of the geometry. Which way is the vector pointing? Like I said, you can continue on. I'll hang out.
Yeah.
If you want me to go back in breakout rooms, I can.
I'm just still not following. Like I feel like I'm right on the border of getting it, but I'm absolutely not getting it. And
So
I'm like, I'm super frustrated. So I got the like sum of fx should be 0. I don't get how I go from like say all 3 angles to solving for T3.
Gotcha. Okay.
And I feel like we did this in 4A, so I feel like I should be able to do it, but
it's okay. And I'm really bummed. I wanted to actually be physically in the lab so I could have a whiteboard to do this. And
yeah.
I haven't figured out how to do this quickly. I don't have like a stylus at home to write on my computer. But if you were to look at the points above weight 1, right? And you have the geometry of the angles of those 2 tensions, what would happen is that you would end up setting up in a set of equations, and you'd have to solve multiple equations here for this. What you would do is you'd say the sum of the forces in the y direction are equal to 0, and those would be the T1 y component and the T3 y component and the weight. So then you would have 2 unknowns there, T1 and T3. Then you would set up another set of equations in the summation of the x components, which would be T1 x component, T3 x component, and of course W doesn't contribute at all. So now you have 2 equations with 2 unknowns. And so then you'd have to substitute in, solve for one, and then go back in and substitute for the last. And if I had a whiteboard, that would be super easy to see.
Let's see. Rob, you had something like T1 cosine theta x. So that would be T1 cosine of theta x would be this angle. So that would be the component of this tension in this direction.
Correct.
And then you have plus Fx1, so that would be the force of x1, presumably in this direction.
Are you working on
Yes,
the
equal and opposite. Yeah.
Equals
So it's
0. So I guess, you know, just trying to get my bearings first. Why would I see Fx1 and know that that should be going this direction, really? Like, that's not obvious to me. Yeah, I would think Fx1, you know, if someone was just to say Fx1, I would say, well, that's probably the positive value. That's probably the component of the force in the x direction, and I would expect that to be a positive.
So actually, the way you've got drawn Fx1, you would actually draw it the other way. They would both go in the positive, and you would sum them up and they'd be equal to 0, right? So then when you solve for Fx1, you would find that T1 cosine theta x would go to the other side and become a negative number. And that would mean that Fx1 was a negative, which would mean it was pointing the way that you've got it drawn. Is that Fx1 is actually pointing in the negative direction, correct?
Yeah, because I have my x.
Right.
With the way I have my
This
x.
is something we go over with free body diagram. So you would still, normally you would put Fx1 pointing to the right. And when you solve for it and it came out negative, that would give you the indication that you had it the incorrect direction. Did I lose you?
Hey, Rob.
Yeah.
I just want to say real quick for everyone in the class, there's a link in the chat right now for the Discord for anyone else who hasn't gotten it. Just to work on labs and homework and stuff.
Okay. All right. So whoever shared, I'm not sure what's going on there.
So Jordan just sent me some of her notes, which makes sense, which she's saying T3 cosine theta 3 equals T1 cosine theta 1. That makes sense because that has to equal 0. And T3 cosine theta 3 equals T2 cosine theta 2. So that makes sense how if you have two of the angles, if you have like the angle for theta 3 and one of the other ones and one of the tensions, that makes a lot of sense.
So all the angles is having to solve two simultaneous equations.
Yeah, and if you had all three angles, then you could just solve for the tensions, correct? Or would you not even need to take that step?
Yeah, you could just solve for the tensions. Yeah.
Can you guys see my screen? I'm not sure if it's working.
It's working.
Sometimes sharing kind of gave everybody sharing rights, which was maybe a disaster.
But real quick though, if we just isolate what's happening around weight 1, we know, and we break it up into its X and Fy. When we're talking about the Fy, we have the Y components are both pointed up, so they're both positive, and then the weight is the force pointed down, right? So we can say T1Y plus T3Y equals weight 1, correct? I believe. And then
yes,
when we
normally would be minus W. So it just moves over and becomes positive.
Yeah. So yeah, or you could say T1y plus T3y minus weight 1 equals 0. That's where this came from. But we could also, and then we talk about the x. Well, T1 is pointed to the left. So we call that one a negative T1x. T3 is pointed to the right. We're calling that one positive. And we know those must equal 0. So then we can say T1x equals T3x. And that gives us more information too. So you could do that for weight 1, and you could do that for weight 2. And T3 should be the same because it's all in equilibrium. So that's another little thing you guys could think about.
Yeah.
That helps.
So somebody was asking earlier, I'm going to post the solutions later this afternoon. I'll have them posted. So you'll be able to look at this, the entire lab.
So if you did want to solve using just the angles, part of that would be you would have to solve for the tensions, correct? First?
Yeah.
Okay.
In fact, the equations that Andrew was just showing, you would need, that would be the equations you'd use, and Tx and Ty would be a function of the angles.
Right.
Okay.
So you guys have 4 equations so far. You have the sum of the forces in the x equals 0, and that's talking about all the forces. So T1, T2, T3. So you have the sum of the forces in the y talking about all of them. So T1, T2, T3. And then you'll have another set of equations that's just relating T1 and T3 with weight 1. And then you have T3, T2 relating weight 2. And with all those, I think you should be able to get whatever you need.
Can you put your screen back up there, Andrew? You share your screen again?
Yeah.
So that you see the sum of the forces of the y, sum of the forces of the x. If you had all the angles, those would be the equations you would use to solve for it. And you wouldn't know T1 and T3, but because you have 2 equations and 2 unknowns, you could solve for them.
Right.
You would have W1. And so then you'd be able to solve your way through to that. But it means solving 2 simultaneous equations. So rather than this sort of direct path that just, one solution after another solution, you have to have a 2-step thing where you'd solve for, say, T1y, and then substitute it into this equation, and then solve for T3, which would be some portion of W.
Right. And so
okay, that makes sense.
Just like how the T1, T3 connection with weight 1, you'd have another set of equations for the T2, T3 connecting to weight 2, right? So you have those 2, and then up here is connecting all of them, and you would also have 0, and you got 0 equals all the other forces in the y. And you'd have to include the weights. So here, I'll just write it, I guess. So you'd have 0 equals T1 in the y, positive. You have minus weight 1. Then you got plus T3 in the y. You got minus weight 2, and then plus T2 in the y.
So you're doing a fairly advanced thing, Andrew. You're doing the entire system at once, right?
Right, and I'm just I'm showing them down here on the bottom. This is breaking the system into little parts, and then up here at the top is thinking about the system as a whole.
So next week we're going to do free body diagrams, and we're going to talk about how Andrew's doing this breaking up or not breaking up, and that'll be really clear hopefully by the end of next week's lab, how to draw free body diagrams of different parts of the system.
Can we submit this a little bit later than 11?
Yes.
Okay. Cool. I got something to attend to for like an hour, and then I can get back, and then I can finish writing it up.
Yeah,
Cool.
that's fine.
Thank you.
Normally
Sweet. It mostly makes sense now. It's just for some reason it's like, I don't know, my brain's still waking up from summer, so. Cool.
So hopefully, yeah, don't make it go too far past, tonight, because being a working dude, the weekends are when I get to grade. So
when I do all my work, I have 2 12-hour shifts this weekend. Anyway.
But you have the opposite problem. Your weeks are free, your weekends are. Anyways, you get the point. So.
All right. Thanks.
And again, my hope is that you're not stuck doing lots of this work outside of lab. I just want to get your brain cranking, and then leave it at that.
Yeah, and then
awesome. Thanks.
I'm gonna head out, but you guys, I think you have access to email me through Canvas. So just like Joanne or Rob, you could email me, and I could try to help you best I can. Also, but I will see you all later. Have a good one.
Thanks, Andrew.
Thank you.
Thanks, Andrew.
Bye.
So Robert, I have a question. So we do have to submit the second part?
No, I'm not asking for the second part. We didn't even get there. I'm not sure what I'm going to do about the second part, whether we're going to tag that on to next week's or not. But no
I'm
part.
sorry. I'm referring to 1B.
Oh, yes. Please submit 1B. Do your best with it. Yeah. Whatever you can.
Okay.
As Isaac said,
Awesome.
I'm going to give you guys some extra time on it.
Cool.
Especially since you're submitting through email rather than through Canvas. Canvas isn't going to bark at you and tell you that you ran out of time.
Mm-hmm.
If you could have it by the end of today, that would be ideal.
We're supposed to be submitting to rowyland at cabrillo.edu, right?
Yes.
Okay, cool. Okay.
Again, this is a big experiment for everybody, I think.
Alrighty. Thanks,
Do you have
Robert.
more questions? Yeah. Thanks, Dave.
Yeah. Take care.
Yep.
Thanks a lot, Rob. Great lecture.
I
Very
think
kind, Peter. Thank you.
I feel like I understood it. Yeah, I think I understood it. So I came up with basically the equations, like I followed your example from the first diagram, how you laid out the equations that at each point. So basically for my diagram, I just did that again. I found the equations for each point. And then basically, I said that you needed just 3 pieces of information to solve the system, basically, or well, to solve for T3, I think is what they were what you were asking for. Yeah. And that's it. Okay, and then I would use, depending on what information I had, based on my 2 solutions, I would use either the equations from the point at one of the weights or the equations from the point at one of the other weights, at the second weight.
That's totally it, Maria. You totally got what I was trying to get. So
okay.
That's precisely correct.
Okay, and then I just wanted to double check in my equations, because now in statics, we're just using cosine the whole time, right?
Yes, you'll bump into the rare occasion where you can't because of some weird geometry, but yes, cosine will save you a lot of problems.
Okay, and so that means our components, all of our, like for example, T2y, that's just T2 cosine theta y2.
Yeah, it will be, I think the way I've drawn theta y2 there is just the angle between the negative x-axis and or did I draw it all the way up to the, it should be from the positive y-axis, really. So it'll be 90 plus whatever that little chunk is. But yeah, you would want the full angle from the positive y-axis down to T2.
Right? Wait, no.
Yeah.
So then
So,
T1.
Let me pull up let me share the screen here real quick again. So T2, I didn't draw the angles on there, but this angle here should be all the way up to there. So it should be, you know, what, about 145 or something. So here's your y-axis. You would come down and go to there. So that would be 145. That would actually be theta T2, or however you want to go. If you drew it right from the x-axis, it would have to be this angle plus 90 degrees. Does that make sense, Maria? I really need to get a way to draw.
Well then, so the T2 component would be T2 times, well, isn't that what theta y is, like the direction angle from the positive y axis?
That's nomenclature. If it was truly the direction angle, yes, that would be correct, because it would be that whole angle.
Yeah, okay, that's what I was thinking.
Yeah.
And
In
then
a two-dimensional sense, that's correct.
Okay. Because when he was doing like the force, when Andrew was drawing out the forces, like I understood that, but then I was going based off of your equations from the first diagram, and that's why I wanted to just make sure that what I wrote was actually the T2y and T3y, or T1x, T2x.
Yeah. Okay.
Okay, I think I got it. Well, you'll see it and then you can tell me.
Yeah, like I said, I'm more concerned about the process than anything else. And
Okay.
you guys are thinking about it, and I'm really happy about that.
Okay, thank you so much, Rob. I'm going to email this to you right now.
Okay. Jason, you got that puzzled look like, what is he talking about?
That for me is a permanent installation.
Okay. All right. How about you, Jordan?
I think I get it. I'm not really sure, but I get it about as much as I did.
Yeah, I think this is a little early in the course. I think in about a week this will make sense.
I hope so.
Let's see. What do I want to do? Yeah, well, let's go back to we were sort of walking through little pieces of it. So if I just start with saying, okay, here's my weight, and that's kind of a vector in itself, I'm willing to say. And then I've got X and I've got my Y here. Where would you put FX1?
So I would draw a unit vector along the x-axis there, a small little chunk, and call that fx.
I would call that fx. All right.
Right. And fy would go up.
And fy would be a little unit vector going that way.
Right. And then, if we're looking at that point, then I would draw T1x and T1y. So T1y would actually go down, and T1x would go right next to fx. So they'd actually both be pointing in the same direction.
T1.
You can draw them separately if you want.
T1x.
Because we're going to look at the x component of T1 and then the y component of T1.
Oh, so T1 is T1x and T2x.
No, T1y.
Oh, yeah. Yep, that makes sense. So T1 is divided into T1x and T1y.
Correct.
And so fx1 is not t1.
No. So at that point,
fx1.
at the attach point, you're pulling on it with a string, right? And that attach point is having to resist that. And now you're saying, well, why did I draw it that way? Why did I draw it to the right? Because you always draw your things positive when you don't know what they are. So if you were
Reasonable.
to sum, if you were to sum the points, right, right where your big intersection there, 0.0, if you were to sum all the x components, which should equal 0, if you write that equation for me, right, sum of the fx, sum of the components in the x direction would be so in the x. So now that would be equal to 0 because it's always equal to 0, right?
And
right,
this is just
0.
This is just for this attachment point.
Correct. Just for point 1.
So just for this point, I have the sum of forces in the x.
Right. And that equals 0.
This is, yeah.
They always equal 0 because it's statics. In dynamics, it'll be a different equation, but
that's right.
So if you do fx, it's going to be that 0 is equal to fx plus t1x.
fx
right,
plus t1x.
Right. So then when you solve for fx, it's going to be a negative t1x, correct?
Because I would think that fx is a positive value.
The way it's drawn, yes. But when you solve for it, if you have 0 equals fx plus t1x, when you solve for fx, it's going to be fx equals minus t1x.
Fx equals minus t1x. Because I would think that these are both positive values from, taken from here, which doesn't add to 0. So that's where I'm stuck. So t1x.
So you've drawn them both as positive. But the reality is that fx has to be pointing the other direction, doesn't it? In order to keep that thing from moving, because otherwise both fx and t1x will make some bigger number that's not equal to 0.
Oh, I see. Huh. Right. So I see. So because I know t1x, well, because I could solve for it if I had t1, then fx, while fx is a vector pointing this way, it's going to be a negative value because it's actually
it actually ends up having to be the other way, but
it's pulling to the left.
Yes.
Yeah, right.
But because of the way we've drawn it, in the convention of drawing everything positive until we know better.
I see.
That's what happens.
So really, yeah, like this is, this is t1x. T1x, and they're
being the same thing. Yep.
Yeah, they're superimposed. But they will have opposite values, which is why they add to 0. That was really what I was trying to get. Okay, that's one piece.
Yeah, this thing about summing the forces to 0 will end up paying dividends in the end rather than to just say fx equals minus t1, which is what most people are initially tempted to do, is to draw that fx to the left and tx to the right and just write the equation that they equal each other. What ends up happening a lot of times is they miss the negative sign, and then when they go to plug those numbers into some other part of the system, they've got the wrong sign.
Right. So I should keep it this way because fx will then, I'll ensure that I don't make that mistake and that fx becomes negative. Yep. So if I had t1, I could solve because t1 is, so I could say this is equal to fx, or maybe another way to do this is fx plus t1 cosine theta x.
Yep, that's it. Yep, you're on it.
Okay.
That's exactly right.
So now I want to sort of play with the question of what pieces of information are essential for finding the forces. Now there are a lot of vectors that I could call forces in this. I could say any one of these attachment points really kind of has 4 forces, right? But I think what you're referring to is just the tension measured on this spring and measured on this spring.
Right. So if you were having to go out there and measure things, you know, what's the least amount of things that you would need to measure in order to solve for the forces, assuming you know the weight?
Yeah. Yeah, assuming I know the weight. I don't know the geometry unless I ask for it.
Yeah. Usually you need to know the geometry, almost always.
Right.
At least on one side. In this case, you need to know the geometry on one side, and then that will determine the geometry on the other side.
All right, let me guess. I'm going to say I need to know, well, if this is 0, 0, then I need to know x2, y2 as a minimum.
Actually, no. Really, all you need to know is theta x and t1, and then you can solve for t2.
Theta x and t1. Is this a knot or a wheel?
That's a knot. It's really, it's not super not critical in that sense, but it's a knot.
Well, it is critical because if you told me that it's a wheel, then I'd say T1 is equal to T2, and I would need to solve for T1 anyways.
That's
maybe
true.
is your point.
Yeah, that's correct. Yeah, it would make life even easier. So yes, not. You're correct. Yeah. So if you do the evaluation at the points where the weight is attached, you have 2 sets of equations you could use.
Yeah, so I was kind of working on that. So
yeah.
These are the 2 attachment points. So I have T1 cosine theta x plus fx1, which I will now, I'll get rid of this and say that fx1 is going this way.
Yep.
And then I'll say sum of the forces y is this angle theta y.
So use the same, yeah.
T1
theta 3 is kind of a weird angle. What you really want to do is you want to measure from the positive y-axis when you use the cosine.
Oh.
For the y.
Yeah, you
so
know what?
Theta, yeah, you don't want to use that angle. You want to use theta x plus 90.
Theta y. Yeah, I'm with you.
Otherwise, that cosine thing falls apart.
Yeah, good reminder. So
I'll be right back, Jason. I gotta pee.
Okay.
Be right back. All right, I'm back.
I'm trying to remember what this is telling me. This is the tension going in this direction. T1.
So when you have a tension, if you were to cut that line in the middle, right? The
Right
part
here?
from the left-hand side would be pulling down and to your right, and the part on the right-hand side would be pulling up and to the left, right? So when you cut a rope in the middle, you kind of have to imagine yourself standing in the middle of the rope, and they're pulling on both of your arms.
Trying to hold it together.
Yeah, and so one would be pulling one way, one would be pulling the other way.
Yeah. Right. Right. So if I was just in this connection point here, if I replace the spring measure.
Yeah, the spring measure is just a way to measure the magnitude of that force. That's all that's doing.
Yeah, with my if I replace that with my hands, then I would be keeping the rope together, and this would be pulling down and to the right, like you said, and this would be pulling up and